Okay, I guess let's start. So we're four speakers, so it's gonna be handheld mic, but hopefully it works. Okay, so understanding your bank data in 100 ms. This is top sentence is really the main purpose of this talk. We're hiring across a number of engineering roles, so software devs, backend, frontend, data, ML. Please go to jobs at entropy.com to find out more. So, and we also have a booth just outside the door. So we'll be there today and tomorrow. Cool. So this is a couple of facts. So every day, currently, there's more than 1 billion electronic transactions happening in the world, and this is growing obviously with the proliferation of internet and crypto and a bunch of other factors. And 45% of these transactions are digital, and this percentage is also increasing, right? Obviously, some fraction will always be cash, but more than half will be digital very, very soon. So, and your kind of probably the closest familiarity with bank transactions is your bank statement, right? So when you log on to your bank online, you see something like this. So previously this was usually sent to you by a PDF or in your post, but effectively a list of your transaction history, right? And up to very recently, the only entities which really had possession of your history and used it for any purpose whatsoever was kind of the large banks, right? So these are the largest ones, but also, just in the US, there's more than 10,000 banks, and all over the world, there's more than 30,000 banks. So this is kind of the classic institutions which took care of your financial transactions, right? But just in the last 5 years, there's more and more companies which are becoming increasingly interested in this data, right? So this is just some of them. Obviously, the largest ones: Amazon and Airbnb loans, Google Wallet, Apple Card, right? Facebook, Libra, then DM, then maybe something else in the future. But a lot of companies are becoming interested in this data. Not only bank, but really any tech company today and in the future. So. What happens is, so of course there is some regulations, right, and some standards associated with this data, right? So there is some ISO standards, and there is some agreements between banks how this data should look like. But the reality is that, the world is big, and there's many banks, and there's many different governing bodies, and there's many thousands of different standards which are evolving over time. And if you take also into account, there's more than 7,000 languages in the world, and bank transactions are not only in English, but in some cases in many of these other languages. And there's more than 200 million companies in the world. Each company obviously has some association with each transaction, right? They're there to make money. Some companies die. Some companies get started every day. And these are some of the numbers I said, right? So 200 million companies in the world, 25,000 banks, 7,000 languages. And just in the US, there's 10,000 new companies getting started every day, and about just as many closing down. So this data, which maybe looks simple and tabular, is actually extremely rich, and more importantly, very, very unstructured, right? So again, up until recently, you really needed two things, right? You needed a lot of common sense and kind of knowledge of real world, and also sometimes, or usually, some financial knowledge to really decipher this data, right? Obviously, you can look at your bank statement yourself, but in a professional setting, it does require a qualified person, and it takes around 100 seconds to understand a single transaction on average, right? Some transactions are quick, but sometimes you really need to figure it out. And this kind of area was, as you can imagine, previously quite closed off for a machine to understand because largely of this common sense factor, right? If you have some transaction to Walmart, how does the computer know what Walmart is, right? I mean, Walmart, you might hard code that, but what about any of the other 200 million companies which just got started yesterday, for example, right? So But really, in the last couple of years, it has actually become possible to reduce that figure by about a factor of 1,000. So, and without sacrifice of accuracy or precision, right? Of using some next generation ML, you can probably imagine natural language models to do this in about 100 milliseconds. And really 1,000 times faster everything, right? So if it took 3 months to get a loan, now it takes 20 seconds, right? If it takes you many years to build up a credit score, now it takes 10 seconds, right? If it took you maybe like 8 to 12 hours to fill in your taxes once a year, now it's, again, a matter of seconds, right? And this has really become possible very, very recently. And so if we come back to the back statement and kind of take one of the transactions out there, right? So these are some of the key fields. Of course, there's more, but these are the important ones, right? So the date, the amount, debit, if it's outgoing or incoming, and then some transaction string, which is sometimes easy to understand, sometimes not. And let's imagine we want a computer to understand this, right? So we want to figure out what's important in there and then make some conclusions, right? Like, what is this spending about? Where did this transaction happen? Who is the merchant in this transaction? And other information. And so to dive deeper into this, we will start with entity recognition. And I'll hand it over to one of our ML engineers and the head of our entity recognition platform, Chady.
Thank you, Ilia. So yeah, as Ilia stated just right now, there's actually quite a few models involved in our pipeline to help you understand and extract some information from our transactions. So the first actually main component that we have is entity recognition. So what is that exactly? Basically, it's just trying to find relevant things in your transaction. It could be like merchants, it could be locations, people, names, or persons. Dates, it could be anything basically. It could be you've got a store number or something and you want to know exactly which store it was. Like anything you can think of and that is relevant could be an entity basically. So let's take the previous example that Ilia showed earlier. So as you can see here, we see AMZN, looks like some Amazon company, US, WA, and this kind of stuff. Like, what are they? When you look them up on the internet, for example, you start to understand that this looks like a transaction by Amazon happening in the US in the state of Washington. That's the general idea that you get after looking up some of the components. So how do we achieve this on our end? Like there's quite a few things actually to do there for having a robust model because as we said earlier, there's so many different formats and they're all like more or less understandable. So first we're going to talk about like how exactly we handle the data that we need for this. So first we need to actually collect the data. So we get like lots of transactions and there's so many of them that a human cannot just like look at them by themselves. So basically we've got our own clustering algorithm. Basically you can check out our Medium article on our entropy Medium on internet. We detail this clustering algorithm a bit more. But basically here I'm going to just talk about what we do with it. So we cluster our data, and what we're going to do is basically look at all those clusters, study them, look at how our models basically use them, and see if, for example, the current model is stable when it's running inference on them. If there's any issues, we also send them to human labelers that are going to check, and we call this actually cluster labeling because the human labelers are not going to look at individual transactions. They're going to look at whole so that they can get more context. Because sometimes transactions, even if they are one entity, they are actually, there could be several transactions that are related to one final goal. Let's say you bought something in 10 different payments and so on. So what happens here is that after all of this is labeled, there's a review process that happens using like algorithms that we have to check like the batches quality and also human reviewers, and it's a cycle basically until the data is good enough, at least for humans. The thing is that like that's not exactly enough because sometimes we've got lots of data for some patterns, sometimes we don't. So what we do is we also augment this data that we collect. Just like some simple ways to do it is like introducing like typos or things like that, replacing entities, even using techniques like mass language modeling to remove words and statistically like replace it by meaningful, actually not entities only, but more like parts of sentences. And yeah, we do this basically, and also like quite a few other things, but those are like some examples. So let's talk about how we train our models. So basically, at least for this specific model, it's an attention-based named entity recognition model. So this one is particular because it has like 2 classification heads, because it's able to understand spans of inside of a transaction, and it's able to then look at those spans and figure out which label it has. So for example, if it's a location, if it's a person or something like that. And we train it with quite a few data. So on some general like name entity recognition data, so that it can understand like common sense and actual real world entities. And then we also train it on a lot of transactional data, basically switching domain by transfer learning. So this model like actually supports quite a few languages. We're training our models to be multilingual because even like, for example, a similar transaction in one country or in even a different, just a different continent, like it can be like very differently written or stated in a bank statement. So our model, by learning different languages, can share information between those languages. And finally, we are trying to make our model like robust to noise, because even if we refine the data that we get before training, it's still noisy. Like it's impossible to get perfect data. We're also trying to make it robust to shifting distribution, because the patterns every time are changing. So we need to continually have the model learn new patterns and data. And also we're trying to make it robust to basically word segmentation, which sometimes it happens that the words in your transaction are like split, or they're like concatenated, and it doesn't really make sense. So you want to be robust to that also. So how do we train it exactly? So you all know the cross entropy loss. I mean, you've maybe most of you have already used it. Well, we don't use that loss on our end. Same, you all know like the mean absolute error loss, which actually, if you look at it real quick, up to a constant, it's actually the same as the unhinged loss, which is stated below of it. And we also don't use that. So what do we use, and why don't we use those losses for training? And what's bad about them? If you look at this diagram here, basically it shows here you see the gradient of the cross entropy loss, and here you can see the gradient of the mean absolute error, or the unhinged loss in this case. And what we can see here is that on the cross entropy loss, there is a weighting term, meaning that samples are weighted differently. And what's the issue with the samples being weighted differently is that if you got outliers or like specifically hard examples or so on, the model is going to focus on them. And also, more importantly, if the data is noisy, meaning it's wrong, the model is going to be like, okay, I'm not able to learn it, so I'm going to try to, the gradients are going to go further in this direction, which is actually an effect you don't want, because it could learn wrong data. So that's one issue with it. And if we look at the mean absolute error, it actually does not do that. So the thing is that cross entropy, it's also interesting for it to like focus on hard elements, right? So we also want to preserve like some of this behavior. Like both of them have like interesting sides, but they also have bad sides. So what do we do? In our case, we use what's called the generalized cross entropy loss. So basically, this loss is a combination of like those two losses. So if like basically Q is 0, then it means that there is absolutely no noise. So when it tends to 0, sorry, because you cannot divide by 0, of course. And when it tends towards 1, it actually tends towards the mean average, mean absolute error. And what happens there is that the loss, depending on the amount of noise that you have in your data set, is going to be able to like to balance a bit more the error. Meaning that if you've got lots of noise in your data set, it's going to be considering all examples more or less equally, meaning that the error will average out. And if your data set is less noisy, you know that you can focus on some of the examples because they are actually hard and not noisy. So there's there's a link to the paper here when we make the slides available, and it's called generalized cross entropy loss. So we didn't stop here. We actually tried to make it even better. So let's take our model. Like it outputs like this, probabilities of its predictions for each entity, and it inputs like the spans. So I just simplified here the diagram for you to see. And what we did is basically we made it smooth. So we're actually smoothing the spans and smoothing also on the entity level. So meaning that if the model, like we don't want the model to be overconfident when it's doing a prediction, because often like it's just going to be a false positive. And that's not something we want. Like it's like every error matters in this case. And with this loss, basically you're able to control the slope you see here, like the way you're spreading out the probabilities of the span and of the entities. And this helps actually make your model less overconfident. And it's an extension to this generalized cross entropy loss. So we're actually doing a lot more things, but like this talk is not infinitely long. So basically, quite a few things that we also work on right now to make the model like more stable and more noise robust. And we're also researching quite a few other alternatives to make our model better, like multitask learning, which is very interesting if you want your model to generalize, prompt engineering, and all of these kind of things. One of the things I talked about earlier is multilingual training. So I'm not going to go too much into details because there's actually a detailed article that we wrote on Medium about it. But yeah, our models like basically need to understand like different cultures and so on. And for that, we developed a method to train our model, which we call like cycling through languages, which basically you train, like it's a very simple method. You train each of your models with their own hyperparameters, their own epochs and so on each of those languages sequentially. And you actually repeat the process, meaning that you can also change the hyperparameters between each steps. There's a lot of experiments that we did here, and we even show some extensions to this method that include, for example, adding translation between languages to do smooth transitions between them and so on. So I'll let you check out the article on our Medium blog. Okay, I talked about training and so on, but of course we need to test our models. Like that's very important, and with so much data, you can always like have lots of false positives and so on. So what do? We've got actually quite a complete testing pipeline, where when our model actually just finished training, as you can see here, we do all the classic stuff like basically just running lots of metrics, F1 precision recall per entity on global entities and so on, just to see where the model is able to perform well or not, and just also get a general like metric on global performance. Then we also test, of course, for regressions against like previous models that we've had in production, because of course we don't want any regression, like otherwise it means that something happened, and we do not want that. So after that, we're actually working currently on a few things, like generating an error report, which will basically lists all the samples per epoch and how like the model, for example, generated labels for them, the loss, and a few other metrics. And also we get the nearest like training samples to those test examples that failed, so that we can check if, okay, maybe we have a training cluster that is bad, and our test sample is bad because of our training and not because of something else. So that's one of the things we do. After that, we are actually working on explainability right now. So by the way, we will be publishing an article on that, on how to generate explainability graphs for name identity recognition models. Yeah, after that, we have like a test set that we should never fail, basically get 1.0 F1. If we fail some of those examples, then it's really bad because there are very important samples. So basically, we're checking for some of our training samples to be always correct. And yeah, of course, like, you know, the usual unit tests and staging, environment testing, and so on before it goes to production. So yeah, that's basically like a glimpse of how we train this model. Now that we've got all those entities, what do we do with them? And you know, what happens next will be presented by Robin with merchant normalization.
Yeah, thanks, Chady. So now, thanks to Chady and his team, we have the different entities in this transaction string. So yeah, now we want to actually produce the data that our customers are actually interested in. So they wouldn't be interested in getting AMZN, but the actual website and the merchant name and some additional information. Yeah, so how do we do that? First of all, there can be multiple organizations found in the string. In this case, it's twice the same organization, but there can also be different ones, like a payment processor, for example. So right now we're just selecting a single organization out of all of those, and we're using different heuristics for those. For example, sometimes there are patterns where it says who the beneficiary is, or yeah, or if the organization occurs first in the string, it's usually the more important one. So there are a bunch of different heuristics. Yeah, so once we selected one, yeah, how do you actually get like the website and all of that stuff? So the naive solution would maybe be to use a big database with different companies and their domains, and then you could do a lookup in that database. But there are some problems with that. One problem you can already see here. So instead of like Amazon Marketplace, that's actually obfuscated, and you only have a few of the actual characters. Yeah, another problem is that you can also see here. So you don't just have Amazon, but you have Amazon Marketplace, and maybe companies have like completely different names sometimes. So that's another difficulty. And another one you can see here, but I'll show an example later, is when you have really companies with very generic names. Just looking up, like finding that name won't really give you much. Like an example here is Napoli Pizza. You probably wouldn't find any company in your big database with that name. And finally, yeah, if you have a static database, you also need to maintain that. Like Ilia said in the introduction, there are new companies showing up every day and disappearing every day. So that's also yeah, a big thing to maintain. So yeah, if all of these problems exist and the naive solution doesn't work that well, so how do we actually do it? So basically, we're making use of search engines and also our internal search. So first, we take the organization we selected. We generate a query, which is right now relatively simple. We just pass on the organization. Maybe we add some more things, like the location, which I'll show later. Yeah, then we do a search, or maybe we already have it in our internal database. So once we have the different search results for that, we're doing some re-ranking to find what the best search result is, or if there is a matching result at all. And yeah, then finally we have the best result. So here's in a bit more detail. Yeah, so we have these different search results and the query, and what we're doing is we're feeding this to a cross-encoder. If you're not familiar with it, it's basically an NLP model where you give it both a query and a search result, and it tells you whether the search result is relevant to the query. So in this example, the first result from Google would be from Forbes, but that is actually not the relevant one. So the second the one with the second rank, the second search result is actually the one we're interested in. And the cross-encoder would tell you which one is more interesting. So it outputs a number between 0 and 1, and 1 is a match and 0 is no match. So we're doing that on all the search results, and then we're both using that for finding the best search result, but we're also thresholding this to see if there's actually no matching result at all. Okay, so we have this cross-encoder, but how do you actually train it? Because you need some kind of data to train it, right? Fortunately, this is relatively simple, and you don't even need to hand label anything here. If you have a data set with companies, there are actually some freely available ones with millions of companies. You can use this, and so they have the name of the company and then some URLs. So what you can do is you can take the name and you can obfuscate it, for example, remove all the vowels or truncate it, and then you can do a search on your search engine that you're interested in, and you'll get a bunch of results. And the nice thing is that from the database or from the data set, you already know what the correct URL is. So with this, you can build a data set that looks like the 2 rows there in the bottom, where you have a query, a search result, and then just a Boolean whether the search result matches or not. And with that, you can train a cross-encoder. So here I have another example where the name is actually ambiguous with Napoli pizza. So if you just Google Napoli pizza, you will find a bunch of results, but likely none of them are actually useful to you. So you can solve this a bit. If you also have, if your transaction contains a location, then we find that with NUR, and then you can actually add that location to your search query, and then you can actually find the correct results. So in this case, once you add the location, actually the 5 top results are all matches. So now we have the URL. How do we actually get all the other stuff we're interested in? For example, the name, the logo, and the different tags. So for the name, what we do right now is we have the title from the search result, and we can just use a few different heuristics to find the actual name. So then we can, in the beginning we had AMZN, and now that we have this title, we can actually get the correct name. So this part is a bit tricky though. Then for the tags, so this is just one example. So we have, again, Amazon.com, and then we're interested in the tags for this. One source is from an internal merchant database where we have a few tags. And then we are also getting it, for example, from the snippet. You can remove stop words, which is basically the uninteresting words, like on or off here would probably get removed. And that's also another useful source for tags. So that's how we get the tags. And the logo, this one is also fairly simple. We just have the URL, and then we have both our internal logo service that has a lot of different logos stored, and we also use external services to get those logos. And so now that we've done this, we have what we were actually interested in. So we went from the transaction with the NUR labels, we went to the name, website, logo, and tags. And from here, I'll hand it over to Johnny, who will present you the transaction categorization.
Hey guys, okay, so I promise I'm the last face up here today, so you don't have to remember all of us. All right, so we have this running transaction example of Amazon, like we talked about before. So previously we mentioned the 2 different parts in the pipeline. So the NARE part where we extract name entities, the normalizer part where we use external resources, search engine to resolve this. And the final part is the understanding part, which is actually understanding at the level of what a human would get out of a transaction. So there are a few different things here, so I'll just cut to the chase. The category here is pretty simple, it's just e-commerce. Usually we want something more fine-grained than this. This is a pretty general transaction, so we can't get very far with it. So maybe not the best example here, but I'll show some examples in the future slides where this can be a bit more pedantic and much more difficult. So a summary of the data task, I mean, this is PyData, it's not PyTransactions. So this is tabular data, and it's not just like rote tabular data, so it's not plug in pandas and play. It's actually a bit more delicate than that. So it's tabular data plus unstructured components. So when you look at a transaction, you see a few different fields here. So there is Amazon Marketplace, 5942, et cetera. This is unstructured text. And then there's some more traditional things. So there's a Boolean for debit credit, which indicates the flow of money. And then there's also an amount, which is 512, which is a float value. So we're not just doing normal tabular data, but we have to combine it with these different structures, which makes this a multimodal problem, which has been pretty hot in the machine learning community lately and is an actual real-world use case for us. So in terms of understanding a transaction, that's even a loaded term itself, there's really kind of 4 different things, and I put some fun icons here to make it a little bit less boring. So we kind of want to know who was involved, who were the parties, why did it take place, and what was actually exchanged. So I'll dive into these a little bit more in depth. So on the left side, we want to know who was involved in the transaction, and particularly who were the parties involved. So we've already covered this for like the last 30 minutes, so I'm not going to dwell too long on here, but the buzzwords you want to get out of here are name entity recognition and information retrieval. Those are the 2 things if you're trying to hire a team to build this, which you put down on your hiring resume. Okay, so the next part is the domain of my stuff, and this is you want to actually understand what happened. So you want to know what was exchanged, or why did it take place, and if you're trying to make use of these transactions for a downstream purpose, the actual inference motive behind it. So broadly speaking, there are kind of 2 different ways this is broken down. So one are lower level categories. They are pretty basic. They describe what happened. And if you just walked up to somebody on the street and said, yeah, I do transaction categorization, this is probably the very first thing that would pop in their mind. And then the second thing would be a verbal action, which is like, yeah, isn't that easy? And then you do something like an eye roll or not, depending on how nice you are, and then explain the next part. So the next part is higher level categories. And this is understanding like what happened and why. So to give you a quick example of what this could be, let's say that you're trying to understand categorization for a business. And the business is very interested in sales, in-person meetings, et cetera. So they have a lot of different expenditures for like steakhouses. Just the actual what happened is money was exchanged, in turn food was brought to a table. But in reality, what was actually happening is those were customer acquisition costs. They were trying to build relationships with the customer, which ultimately went down into their budgeting for that quarter or whatever for acquiring new customers. So understanding this is more of a human understanding task, which puts us into this regime of modern machine learning and understanding things at a more complex level. Okay. So I had no idea the Hugging Face was on before us, so the emoji is unrelated, so I apologize if any of you guys are still in the room. But anyway, so text classification is supposed to be easy, right? I mean, just like toss our naive days, call it a day, and then we're done. So great. We can just end the talk there, and I'm like almost over time anyway, so we probably should have, but that's not what's going to happen. So there's actually more to this. So we'll dive into some examples that are a little bit more difficult. Right here, I have a transaction that is basically the same thing, but repeated 4 different times, and I chose my alma mater of UCLA to illustrate the point. I'm advertising 2 things, Entropy and UCLA. Okay, so the transaction here is just going to talk about the school. And in general, transactions look like this. They have an entity, like we can do all of the great things we talked about, and our team has done a really outstanding job building earlier. So we can identify, like UCLA is right here. We can identify ID numbers. We can say, look, it was an external transfer. We could even find the date. So we can do all of the fun entity recognition. But the problem is that we really don't know what this was for. And the different parts of tabular learning now start to play a really critical role. It's not just an NLP problem. So if you look here, the things that are shifting are amount and entry type mostly, and the text actually doesn't really matter. So in the very first example, you have an incoming payment for roughly $16,000. And anybody that has gone through a schooling system knows this is probably some kind of disbursement. So maybe the recipient like had won a grant or an award or has some kind of loan. If the amount is a little bit lower, like say in like the 2,000 to 3,000 range, I'm not going to say what my student, my salary was as a graduate student, but it can be in this range, and it's a totally different interpretation. If it goes even lower, then all of a sudden you have a very different picture of what happened. So oftentimes, if you purchase something at a large place like university, it doesn't matter what you're purchasing. So if you go to a campus bookstore, you go to a campus coffee store or whatever, it all gets billed in the transaction statement as following from the university itself. So in this case here, $6.99 is actually most likely to be something like coffee. And then finally, we'll do one more example, which is very similar. Like I just said, if you raise that amount just a little bit higher to 160 and make it outgoing, it's very likely it becomes a textbook. So what has now become a simple problem is actually quite difficult because the reality is that when we do transaction categorization, we are bringing in a ton of external common sense knowledge. And this is exactly what Ilia had brought up before, which is we need to teach our models to have a basic understanding kind of like of how human society interacts, like how economies work, how much goods and services cost, what their value is when there isn't like insane inflation, which I guess is a changing distribution thing that we have to deal with as well, and all of this. Anyway, so I guess what makes this hard is that we also get a lot of this is incomplete data. So we can't even definitively have transactions that are as clean as the example I gave you before. So in order to solve this problem, we do a few things. So we build natural language models that are capable of these complex, higher level inferences. And then we also add in additional queries. So we use attention-based models that have the structure to attend on and be able to bring in the arbitrary complexity that we need. We also put in multimodalities, as we talked about earlier, and that's easily put together with NLP. Almost there, so we also do multitask learning, and this has been kind of the emergent trend in the last couple of years with machine learning, is that you can solve very difficult tasks by creating many different tasks, each of varying level of complexity, and it turns out that transactions actually have multiple different views associated with them based on who the account holder is, and this gives a very rich thing. And then finally, here's a plug for this thing called custom models, so some graphs here. Basically, you can tune things yourself. It's really fun. I made them. Here's some fun TS&E, and this is more about our culture, and we're hiring, because remember, that's the point of this talk.